Chapter 7 focuses on areas, in particular, determining areas under the curve. We already discussed how this is one of the central problems in integral calculus, and then we took a little bit of a detour to study discrete dynamical systems. Now, let's recall what the problem at the core of integral calculus in this particular description is. If you have a function y equals f of x of some shape and an interval between a and b, the idea is to be able to calculate the area under the graph of the function between the two given endpoints. Now, if the function you're given is a straight line, for example, then the computations are going to be fairly easily. What calculus techniques allow us to develop, though, are computations for irregular shapes, where the function is, while differentiable, curvy, smooth, and not a straight line. We see lots of applications to these ideas, but in particular, for example, in medical study. So my daughter in December of 2020 had a perforated appendicitis, and this is actually an ultrasound of her abscess near her appendix. As you can see, the measurements that are taken are across the widest part in each of the two dimensions that the ultrasound can see. When I spoke to the technician, they did mention that if they were to try to find a volume of the abscess, which isn't normally done for abscesses, but is often done for things like hearts or tumors, then they would in fact do what the techniques that we're going to develop in this chapter to manually calculate the volume of such a thing. As you can clearly see, this is a highly irregular shape, so this is not something that we have a formula for. Let's start with some shapes that are easily describable with functions and talk about the areas under the graph of that function on a given particular interval. So between 0 and 2. One of the first things we can do, so first of all, let's discuss that we want this particular area under the graph above the x-axis. One of the first things we can do is, of course, eyeball it somehow, right? Each one of these squares has an area of 1, so I can try to figure out really roughly what the area is. The next best thing is to maybe split my full interval from 0 to 2 into some number of subintervals and then see what I can do there. Recall that when we started discussing areas, one of the most basic, or rather the most basic area that we know is an area of a rectangle. So if I can somehow fit a bunch of rectangles under this parabola here, maybe if I make them skinny enough, it will be a good approximation. What I'm going to do is try to develop a method that systematically makes these calculations possible. So let's start by taking our interval from 0 to 2. And for our first example here, let's suppose that we're going to split it into 4 equal pieces, each of size of width 0.5. And then what I'm going to do is on each one of these pieces, construct a rectangle that will fit under my parabola. Now again, I'm going to want a systematic way of doing so I can generalize this method and not just haphazardly create rectangles. So for my first picture here, what I'm going to do is to construct left endpoint rectangles. Let's see how that particular method works. If I've decided to split everything into 4 pieces, I'm going to take a close look at each piece one at a time. So for this particular piece, if I'm using left endpoints, I'm going to look at the left endpoint. I'm going to go up to the function at that endpoint and construct a rectangle of that height on that interval. Now, my first rectangle here is not very interesting because my graph actually goes through the origin, so the height of this particular rectangle is just 0. The next one is going to be a little more insightful. So for the next interval between 0.5 and 1, again, because I am using left endpoints in this particular case, I'm going to take the left endpoint, go up to the function, and then use that as the height of a rectangle that I construct over the entire width of my little subinterval. So left point up to the function and then span that rectangle through my entire interval. Let me make it look a little more straight. There we go. So this is going to be my second rectangle. I'm going to do the same thing for the next little piece. So between 1 and 1.5, I'm going to take the left endpoint, again being consistent throughout, go up to the function and span the rectangle over the chosen little subinterval. Span the rectangle this way. Okay, and for the last one, from 1.5 all the way up to my function, across and down to construct rectangles. Now, the idea is that the sum of areas of these little rectangles, which is something I can easily calculate, approximates the area that I am actually after. Now I can see that this is not perfect. I'm missing quite large chunks here and there, but this is the first step in developing the process. Let's actually figure out what the number is here. So what I notice is for each of the rectangles, the width is going to be 0.5. So the area of the first rectangle is 0.5. That's its width, times its height. Now for the first rectangle, what I did was take the left-hand point and look up where the function is. If I plug in 0 into x squared, I'm going to get 0, so the height of this rectangle is just 0. Then I'm going to add the area of the second rectangle. The width of it is still 0.5, because the width of all of them is going to be 0.5, but now I have to figure out what is the height here. Well, what I did was take 0.5, which is the left-hand point, and look up how high the function was. How can I figure out the height of this rectangle using the function that I am given? Well, all I need to do really is figure out the y-coordinate here, so I can take my left-hand point and plug it into the function. So for the first one, I'm going to write it out carefully. I'm going to plug in 0.5 into my function, and this will produce the height of my rectangle here. Okay, let's go through the next one. So for the next rectangle, what am I going to have? The width of it is still 0.5, but now what about the height? Well, I took 1, I plugged it into my function, and I got the height of this rectangle. So 1 squared. Plus my final one here, the width is still 0.5, but now the height is I have taken 1.5, plugged it into the function to figure out the height. So 1.5 squared. Okay, I can of course I can calculate what these numbers actually are and also label the corresponding rectangles. So this is going to end up being 0.25, this one is going to be at 1, and this one is going to be at 2.25. So if I want to calculate the final number, I'm going to plug these values in and plug this entire thing into my calculator. Now, the other thing I could have done, even if I decide to still think about 4 rectangles, I could have used the right endpoint in order to construct my rectangles and calculate the heights. So let's do that and see how the overall picture will differ from the first one that I've constructed. Again, make sure you're being consistent throughout. If you're picking the right endpoint, then you're picking the right endpoint for each little interval that you're considering. So between 0 and 0.5, this is my first interval, I'm going to take the right endpoint here, go up to the function, and then construct the rectangle spanning the interval that I chose. So in this case, it's going to be a little rectangle this way. Start with 0 to 0.5, go up to the function on the right hand point, and then span my rectangle over that little region. There it is. You can already see that this is quite different from the rectangle that I've constructed using the left hand point. And I'm going to proceed the exact same way for the rest of them. So from 0.5 to 1, I'm going to take the right end point, go up to the function, and then span my rectangle over that region. Okay? Consistency here is key. Keep reminding yourself that you're going to use 1 point for every single subinterval. 1 to 1.5. I'm going to go up to the function here. Maybe a little bit of an overshot, something like this. I mean, your sketch here doesn't have to be exact because we will figure out what the actual heights are by plugging it into the function and getting the exact solution. So, but a good sketch is really providing visual support of the fact that this is a reasonable method to use. Now, between 1.5 and 2, my right end point is 2. I go up to the function, across my little interval, and then down to construct the rectangle. Now, of course, I can calculate the areas of these rectangles in the exact same way. I've just calculated them using left endpoints, but mindful of the fact that now my heights are going to be determined by the right endpoints. Now, notice that some of the numbers here are actually going to repeat themselves because, in fact, you're using the same points, you're just constructing the rectangles into the opposite direction. What I notice, though, here is in this particular case, for the right endpoints, my rectangles always cover more area than fits under the parabola. So while this method will produce an underestimate of the area under the parabola, this one will clearly produce an overestimate of that. And if we calculate the numbers here, this will end up being 1.75, and on the right hand side, you're going to get 3.75. Please do go through the actual calculations for the area of each single one of these rectangles to make sure that 3.75 is what you get for the total area covered here. Now, with 4 rectangles, this is a reasonable picture to have, but of course, we can see that the area we want to cover isn't exactly what ends up being covered by the rectangles that we construct. The idea, though, is that the more rectangles you construct, the closer your approximation is in fact going to be. And this can be easily seen if you just draw a few of these rectangles by hand, or if you use technology to help you visualize something like this. So this particular Desmos calculator does the what's called Riemann's sums for you. So here is the exact same picture that we have just seen. Let me maybe zoom this in a little bit. And what we see here, first of all, are the left endpoint rectangles, 4 of them. If you want to see the right endpoint rectangles, we can see them here as well. Here they are. This corresponds to the pictures that we've just built. There are a number of other different things that you can do. For example, you can construct midpoint rectangles. So here I still have 4 total rectangles, but instead of picking the left endpoint or the right endpoint, I choose the middle of each interval to actually focus on. This is also quite possible and one of the methods that is used quite often. Now, the idea is, let's say we stick with the left end intervals, is if I increase the number of rectangles I'm constructing, my approximation is going to get better. So this is already 7, this is 10, and so on and so on and so on. By the time I get to 50, you can see how the area covered by the rectangles, which is green here, is a really good approximation of the area that the parabola actually contains underneath itself and above the x-axis. This is what we've developed things like summation formulas for, because what we're going to do in the next class is take our rectangles and let n, the number of them, tend to infinity to make our approximations better and better. Now, before we do that, we're going to practice a little bit more with the shear constructions of the rectangles, because there's something else that we need to acquire quite a bit of intuition for. So here I have a different function. My function is a cubic, x cubed plus 1, and I consider it on the interval between 0 and 2. 0 and 2. I have 2 things I would like to do: compute the total area covered by 4 left rectangles, and then compute the total area covered by 8 right rectangles. So how are these pictures going to be different, and what are going to be the corresponding answers? Let's start with constructing the 4 left rectangles. If I go between 0 and 2, 4 rectangles means, just as the exercise before, I'm actually splitting this entire region into 4, and then for each one of them, I'm going to take the left hand point, go up to the function, and then construct the rectangle based on that height. Okay? I strongly encourage you to pause the video here and actually construct the rectangles for yourself, the 4 left ones and the 8 right ones, just to see how the construction is actually going to work out. Okay, so assuming you've been a good student and have done just that, pause the video, have gone through, what you will see, for example, for the 4 left rectangles, is that you should have a picture just like this one. For each of the 4 endpoints, I'm going to construct a rectangle spanning that particular subinterval. And I can, of course, easily calculate what the points here are by simply dividing the length of my entire interval from 0 to 2 into 4 pieces as instructed. Now, if I were to calculate the areas of these rectangles, then what I'm going to do is something very similar to what we've done in the previous exercise. So for part A here, I'm going to note that the width of each rectangle is going to be 0.5, and then in order for me to calculate the heights, I'm going to use the left endpoint of each interval, plug it into my function, and figure out what the y-coordinate or the height of the corresponding triangle is. So for the first one, I plug 0 into my function. Don't just guesstimate from the graph. We have a function so we can calculate the exact number. I plug in 0 into here. I can easily see that it's going to be 1, but I'm going to write it out fully because this is one of the first examples that we're doing. For the next little rectangle, this guy, I'm going to do the exact same thing. The width is still 0.5, and then I'm going to take its left endpoint because those were the endpoints that I was using. So 0.5, plug it into the formula for the function, and calculate the height of the corresponding rectangle. I'm going to do the exact same thing for the for the third rectangle. I'm going to plug its left endpoint into my function to calculate the height. And then finally, one more. My last rectangle's left endpoint is 1.5. I'm plugging this into a function to calculate its value there. So what we actually notice is that 0.5 is going to be common to all of them, so I can even factor it out. And what I'm going to have left are just calculations of the function values at the 4 endpoints that I'm using. In this particular case, the left ones. For the second part B here, it's asking to calculate the area covered by 8 right rectangles. Now let's pretend just for a second that I don't have the graph of this function in front of me, and all I am given is the formula, the interval, and the fact that I want 8 right rectangles. If for some bizarre reason I don't have Desmos in front of me, as I know you all do, I can still do this question without having to draw the actual graph. Here is how I'm going to approach it. I would like to draw something just because I really prefer visual techniques. So all I'm going to draw is the region between 0 and 2. This is the interval that I know I am working on, and I'm going to have to split this guy up into 8 sub-intervals. So into 2, and then into 2 more, and into 2 more. There's 8 of them all together. Let me move this down just a little bit. Okay, now I can figure out what the width of each one of them is going to be because I know that the total width of my interval is 2, and I'm going to have to fit 8 of them in here. So 2 divided by 8 is a quarter. So each one of these guys is going to be 0.25 long. And that means I can also label them. So 0.25, 0.5, 0.751. Now, I know that these calculations seem very easy so far, but that's because we're working with small numbers like 8. If I asked you to split this into 60, you wouldn't be able to just pop the scale on. You'd actually have to figure out what it is. Now, if I'm going to use the right rectangles, that means that for each little subinterval, I'm going to take the right endpoint, plug that into my function, and calculate the actual height of the rectangle. Now, I'm not seeing the rectangles here because I'm pretending I don't have the graph of the function, but for each one of these guys, I can easily see what the right endpoint is going to be. So let me write a few of them down. So for the first little rectangle, what I'm going to get is its width, which is 0.25, as it will be for all of the rectangles in this case. And then the right endpoint goes into the function to calculate the height. So 0.25 cubed plus 1. For the next rectangle, I am still going to have 0.25 because that's the width of all of them. But for this next rectangle, the right endpoint is going to be this one. So 0.5, that's what I'm going to plug into the function. 0.5 cubed plus 1. and so on. I proceed through all of them. Now you notice that even with 8 already, this is getting annoyingly cumbersome because I have to do very simple calculations, but I have to do them over and over again for some obnoxious number of cases. This is just 4, and I'm going to have to produce 4 more. And this is, again, what we're going to focus on, how to make these calculations more efficient, if not more precise. Now, I encourage you to finish this off just to get a practice with plugging in the consistently the right endpoint as you are required, and then see how that goes. I also encourage you to then actually draw these triangles on the graph. What this is supposed to illustrate is that we don't need the graph to carry out these calculations, but a visual support of the graph is always something that can be very useful for these questions here. In particular, the visual support can be useful if the graph falls below the x-axis. So let's see what happens here. This is the graph of x squared minus 1, and again on the interval between 0 and 2. We're asked to compute the total area covered by the 4 left rectangles. So let's see what happens here. I still have 4, so I'm still splitting my interval into the exact same 0.5, 1, 1.5, and I'm going to construct left endpoint rectangles. So for the first guy, from 0 to 0.5, I'm going to use the left endpoint to go to the function and construct the rectangle that spans my chosen subinterval. So notice that this is the first case where I'm not going up to the function, I'm going down to the function because my function happens to be down from where the x-axis actually is. This is my first little rectangle. Great. Next one, between 0.5 and 1, I'm going to use the left hand point again, as instructed, go to the function, which still happens to be down, but that's okay, and then span my rectangle over the given region. So my second rectangle is going to be like this. I even noticed that my third rectangle is still going to be below the x-axis because the left hand point of my next region is still going to lead me toward the negative side here. And then finally, for the last little region, I am going to go up to the function. Now it's going to be a little shorty guy here. There we go. Okay, so these are my rectangles. Great. Now let's actually calculate the area covered by them. So first of all, let's label our endpoints here so we can easily plug them in. And then notice that I have a small typo here. This should be a 2 in the formula for the function. As I can see, my parabola has a negative 2 as a vertical shift. Okay, so for each of these rectangles, the width is going to be 0.5. So for the first one, I have the width is 0.5. And what about the height? Well, I'm going to take the left-hand point because those were the points that I used to construct the heights with, 0 in this case, and plug it into my function. Remember that, as per the last example, I don't even need the graph for it. I know that I'm simply going to take the left-hand point, plug it into the function, and that's going to give me the height. So what are we going to have here? 0 squared minus 2. Now the numbers here are small enough for me to notice something a little bit odd, namely the fact that 0 squared minus 2 is going to be minus 2, so negative. So this height is in fact negative. Now this is visually supported by the graph because I did go below the x-axis to get to the point on my function to be able to construct the rectangle at. Now this means though that the area of this first rectangle here is going to count as negative. And this is a very important distinction. You don't get to make all areas positive. The height is computed purely from the function. So if the graph happens to lie below the x-axis at some points, then the rectangles that fall below the x-axis will be counted as having negative area. What these summations, the Riemann summations, are going to give you is so-called signed area. It has a sign. If it's above the x-axis, it's positive. If it's below the x-axis, it is negative. This is something we're going to have to be careful about in the next few lectures. Okay, but this doesn't really affect our method in any way. In fact, this is what keeps our method consistent. All you have to do is pick a point and plug it into the function. If the result happens to be negative, so be it. So let's see what happens with the rest of our rectangles here. For the next one, I pick the left-hand point. So for the second guy, the left-hand point, I plug it in here. I'm going to get 0.5 squared minus 2. The next one, the next rectangle, has 1 as the left endpoint. I will plug it into here, 1 squared minus 2. And then the last one has 1.5 as the left endpoint. Plug it into here, will give me 1.5 squared minus 2. So if I actually calculate this entire sum, if I add all of these guys up, I'm going to get negative 2.25. And we can see from the graph that in fact, most of my rectangles do lie below the x-axis, with only this last little short guy lying above, which means that I do expect the total area to be negative. Again, if the calculations give you the negative area, then the area is in fact negative. So be careful about that. Do not simply make this into a positive number. The areas produced by this method are signed areas. Now I'm going to leave one more example for you to do. It's the exact same function. So again, notice the typo here. It's the exact same function, except now we're using a different number of rectangles, 6, which will actually make them fall onto sort of pretty grid blocks, and I'm gonna want to use the right rectangles. So every time you're constructing a rectangle, you're gonna use the right endpoint to actually construct a rectangle and then span it over your region here. This is for you to do to practice both calculations and sketching these rectangles before we move on to generalizing these methods.